Hi, my name is Megan Hesse, and I am a sophomore chemistry student at Western. And today I will be presenting on the use of surface-enhanced Raman spectroscopy to monitor reactions with the pesticide Paraquat. Before we get started, there's a few people I need to thank. This project was funded in part by the WKU RCAP 28016 with additional support from the WKU Department of Chemistry. And I also want to give a special thanks to Dr. Matthew Nee, who is my faculty advisor, and he's been super helpful in getting me started with research and really guiding me and guiding my projects. And I also want to thank Ryan Lamb, who is a master's student in the lab, and he's been so helpful to me and teaching me about his research, his projects, and also all of the technical lab stuff. He's just been a really big help to me. So to get started, there are harmful pesticides being introduced into the environment all the time, and one major cause of this is pesticides in agriculture. These pesticides can be very harmful to people and animals when introduced into our water supply, or also if we eat it when it's on our food and stuff. And so this is a major problem. And so one way to remove these harmful pesticides or other chemicals in our surface water is through photodegradation. And what photodegradation is it takes UV rays from the sun and a photocatalyst, and it can neutralize or break down these harmful pesticides and other chemicals. And so this is a proven way that it does remove these chemicals from the water. But what hasn't been done is we haven't been able to actually monitor this reaction in real time. And so that's what we're trying to do. And it's important because it gives us kinetic information about what is actually happening when in this reaction. And we plan to do that by using surface-enhanced Raman spectroscopy. And so what Raman spectroscopy is it's a type of spectroscopy that uses vibrational modes. So what it does is a laser beam strikes the analyte, or the thing that we're looking at, with a laser, and after it hits it, it bounces back with a different frequency. And so our spectrometer can read the frequency it sends out versus what it got back after it struck the analyte. But the one problem with this is that there's a low signal to noise ratio. So the signal doesn't come out of the noise all the time, and it's kind of hard to differentiate what's actually a Raman peak and what's just like a loud noise peak on there. So one way that we fix this is through surface-enhanced Raman spectroscopy. And so what happens is the analyte gets attached to a metal surface. In our case, we use gold nanoparticles. And this really increases the magnetic field surrounding the analyte. So when the laser light strikes the analyte, the frequency coming back has much greater intensity. And so in lab, what we do to start is we have to synthesize the gold nanoparticles. So we start by heating gold-3 chloride trihydrate, and then when we add sodium citrate and heat the solution, then the sodium citrate reduces the gold-3 just to elemental gold, and then we're left with these little nice gold nanoparticles. And so this image here is a TEM image of our gold nanoparticles, and they're about 20 to 50 nanometers, which is good. It's the size we're going for and helps with good SIRS. Another problem with using this SIRS is that sometimes the signal does not stay constant over time, and this is due to the nanoparticles over aggregating. The gold gets too big and it no longer stays suspended in solution, and it falls out and clumps together at the bottom. And so how we can stop this problem is we add sodium dodecyl sulfate, or SDS, to the solution. And so without the SDS, they clump up together, but with the SDS, it lets them clump just a little bit, but it caps the aggregation due to the molecule having a very polar end and non-polar end. So it'll stop the aggregation and not let too many fall together. And so we've seen SDS successfully stabilize rhodamine 6G, which is a red dye that also is harmful in the environment. And so with no SDS added to the solution, when we look at the Raman spectra, we see that it's each peak slowly decreases over time, and after about 20 minutes, it's not really usable, and you can't see any real differentiation or any Raman going on there. But when we do add some of the SDS, we can see in this graph, it's a graph of all the different areas of the Raman peaks. So we can see that it decreases just a little bit and then stabilizes almost completely. And so then we can be able to track reactions with the stable Raman signal. And so we've also been able to see reactions happening with rhodamine 6G. So this is also, we just picked one specific peak on the spectra and they all act the same. So this lighter purple line up here is the starting peak. And so when we add sodium hydroxide, a new peak increases at about the 12-minute mark is when we added it. And so the change in that Raman indicated that there was a structural change that happened there. And then we added hydrochloric acid after, and when that peak disappears, that indicated to us that another chemical reaction was going on. And so we thought it worked good for rhodamine. Let's try it for paraquat too. And excuse me. And the signal was still relatively unstable. When we did add SDS, it stabilized it more so than without, because also it dropped off at about 20 minutes when we did it with nothing at all. However, we still need the signal to be more stable if we do want to adequately monitor the photodegradation of the molecule. So in this graph, we can see this is with 800 microliters of SDS, the signal still decreased over time. So we've tried, well, let's tweak the concentration of our SDS and see if adding more or less will be helpful in capping them. And we did find that the SDS, and we did find that adjusting the concentration of the SDS did not completely stabilize our Raman signal. And so when we decreased it just a little bit, we found that it was about the same results, and we got about 40 to 50% of our original peaks, but still we can't really be able to monitor reactions with that. And so then we thought, well, let's increase the concentration and then maybe we'll get better signal too. However, that was actually worse. And we ended up with like 60 to 40% of the original signal. And having the stronger concentration of SDS, the decrease in that signal was probably due to ionic strength. SDS is an ion, so there is a charge with it. So the more ions you add to solution, the greater the ionic strength, which would probably also cause the nanoparticles to fall out of solution. And so in conclusion, we still cannot monitor the photodegradation of paraquat until that surge signal is stable. And in our experiments of adjusting the concentration of SDS, that wasn't successful in completely stabilizing the signal. And so we may need to do a few more experiments. We think that the next step to go is to adjust the concentration, because that might affect ionic strength and leave it in solution more. And so, okay, that's my presentation. Thank you very much.